Let's take a look at concatenation and alternation and closure a little bit more concretely. So the simplest operator that we previewed before is concatenation, right? And any two regular expressions can be concatenated together. It doesn't just have to be one letter concatenated with another. We can take any two regular expressions and effectively join them together such that one regular expression has to be followed by another regular expression through concatenation. And as I mentioned before, the way that we write this tends to be that we'll just write one after the other, as you're seeing here, right? So R1 followed by or and then R2. And if you were to look at research papers, you would notice that they might use the dot operator between these two to explicitly say that there's the concatenation operator. But we are assuming implicitly that there is a concatenation operator between any two regular expressions that are written side by side like this, all right? And what can we do with this? Well, if we imagine an example where we have a regular expression R1, say, is C, and R2 is, say, O, we can take R1 concatenated with R2, right? And that would be C followed by O, right? And there's no real magic here, right? So let's imagine we're naming this R prime, right? So R prime we could define as a new regular expression, right? That is CO, or those two concatenated with one another. And then if we had some other regular expressions like R3 is M and R4 is P, we can imagine that R prime concatenated with R3 concatenated with R4 is this regular expression COMP, right? C followed by O followed by M followed by P. Hopefully this doesn't feel too mind-blowing. But what we're saying here is we can join two regular expressions together. These all just happen to be very simple regular expressions. But as we've seen already, there are some other operators we can use to build more complex regular expressions. And concatenation can generally join two regular expressions together such that the first one must be followed by the second one in order for there to be a match. And again, the way that you'll read this is the and is as and then or followed by. This should really feel pretty natural and obvious. This is what you use whenever you search a web page and you hit Control F and you type in a string of characters. Those characters are forming a regular expression where each character is followed by the next, and that's the pattern that you're looking for in a web page to match. We can try this out by switching to the terminal and CDing into the directory that has a file that would be fun to use regular expressions with, which is the user share dictionary, or dict for short, directory. And we looked at this earlier in this semester. In this directory, we have our dictionary as American English, and then there's this symbolic link to the American English file named words. It's a little bit shorter and easier for us to use. So we're just going to use words, right? So if we were to cat words into the head program, we would print out the first 10 words in that file. And we see that, again, this is just a plain text file where each line has a single word in it. And we can use this to play around with regular expressions. Right? So we are going to cat words and pipe that into the grep program. And grep stands for global regular expression print when you find a match, right? The global part is kind of an antiquity, but the regular expression is what we're talking about right now. And the print just means it goes back to the idea that anytime you find a match, we're going to print out a match to standard output. And we are going to use the extended syntax of grep. This is a more modern syntax that actually mirrors the way that we're going to be annotating our regular expressions in class. And this is also tends to be the syntax that you would use to specify regular expressions in modern programming languages, such as JavaScript or Python or Java, and so on and so forth, right? The standard or old traditional, 70s mode grep, you have to be a little bit more careful about how you escape certain things. But that's a little bit beyond the scope of what we're talking about. So let's specify a pattern here. So the pattern that we just searched for was C concatenated with O, concatenated with M, concatenated with P. So if we run that command and pipe the output into grep, grep is going to print only the strings that match that regular expression we just searched for. And sure enough, we see that there are a bunch of words that contain this regular expression in them. And grep by default in our environment here is highlighting those matches in red. So where it found a match with our regular expression, it's highlighting that in red. Similarly, we could search for, say, the regular expression W followed by O followed by W, and notice that we're getting the matched words against that particular regular expression. All right. Hopefully this is, again, the same as Control F. We're just searching in an exact match of a sequence of letters following one after the other. But where regular expressions get much more interesting and powerful are in the alternation and closure operators. So let's go take a look at those. Alternation, again, is the vertical bar. And if we were to specify this more formally in terms of set notation and how a computer science theoretician would, we would call this the union operator, because we're taking the union of two different regular expressions and saying either one is going to be valid. Again, that's something you'll explore later in the theory of language and computation course. But if we have two regular expressions, R1 and R2, we can alternate them, or we can take the union of them with R1 followed by the vertical bar, or you would say R2. And this symbol tends to be pretty universal. You're going to see this used everywhere that alternation comes about. And so just like the previous example where we had R1 is the character C, R2 is the character O, we can form a compound regular expression, R prime, by saying R1 or R2, and that would give us C or O as our regular expression. We could similarly say, okay, well, let's alternate, form an even more complex with R3 being M and R4 being P. So R prime or R3 or R4 would result in a regular expression where it's C or O or M or P. The best way to read this is as or, right? And this operator should not feel natural. I should actually fix that on the slide real quick. You're seeing some of this come together live. This one does not feel natural. All right. And let's go try this out in grep, right? So this one doesn't necessarily feel natural at all because it means we're searching for some subset of characters. So I'm going to clear my screen and say, okay, if we search for C or O or M or P, right? And I hit enter here, there are going to be a ton of matches because this is going to be any word that matches any of those four letters, right? In fact, I'm going to hit Control C and it's going to take a while because of how buffering is set up for this program to actually exit, but there we go. And so notice that we have O's being matched. They're disconnected from one another. OOM is there. We see some C's matching. So any word that had any of those four letters in any order would match. All right. But let's try something a little bit more interesting. Let's try the example from the previous video where we had wow or bam. All right. So wow or bam, and notice we're matching Alabama, Obama, bamboo, powwow, powwowed. And so notice that either the concatenation of a W followed by an O followed by a W has to match, or a B followed by an A followed by an M has to match. And so what we've done is we've taken these regular expressions and notice these are non-trivial, right? This is two concatenation operators in wow, two concatenation operators in bam. If this was R1 and R2, then we would form a new regular expression that is either wow or bam by using this alternation operator, and it will match either of those two things, right? So let's look at the last of these three operators, which is the 0 or more repetitions, or the closure operator, also known as the Kleene star. So closure is the formal name for 0 or more repetitions. And any regular expression R can be repeated 0 or more times with R followed by the star. Right? The asterisk symbol is formally called the Kleene star, and that's named after its inventor, Stephen Kleene, I believe back in the 40s or early 50s. And this is a universal symbol that you'll see all over the place in terms of regular expressions and how we specify 0 or more repetitions of some regular expression. Right? So if R is the character C, so if our regular expression R is C, we can repeat R 0 or more times with C followed by star or R followed by star. They would have the same meaning in this simple context. And the way to read this is something, whatever comes before the star is repeated 0 or more times, right? So this is a weird operator in isolation, because if we just have C followed by star, that means match either nothing or any number of C's one after the other, which would match a whole lot of things. But when we combine this with other operators, it becomes very powerful. So let's take a look at this. So I'm going to clear my screen, and I'm going to, let's try this in isolation. So C star, right? And notice that we're going to match every word. And I tried to kill this. We'll see how long it goes before it actually gets my signal. And it matched every word because we can have 0 C's and this is still a match, right? But it also matches single C's and more than one C followed by one after the other, right? So 0 or more repetitions of a C is what this pattern matched. That's kind of weird, right? 0 or more doesn't seem to be too helpful, right? So let's try and imagine how we might compose this with another operator to be more interesting. So let's say A followed by 0 or more C's. And once again, this is going to match a number of things because it's going to match the character A in isolation, followed by either C's directly. And then here we're saying 2 matches, right? So this would be A followed by a C, and that's 1 match against this regular expression. And then we're matching again as a new instance of this regular expression match right after it, right? So that still doesn't quite get us there. But what if we did A followed by a C followed by 0 or more C's? So this will match a C, or it will match a CC or ACCCC if there was a word that involved that. And if we scroll up, we can see that we're matching, sure enough, A followed by at least 1 C. And here we have vaccinated vaccines, which is A followed by 2 C's. I don't believe there's any English word that has 3 C's after one after the other, but you can imagine that if there were, we would see that they would match here, right? So one other example we can imagine is, well, what if we had A or O or I or U or E followed by A or O or I or U or E 0 or more times. So this would be 1 vowel followed by 0 or more vowels, one after the other, right? And so this will match, again, a number of words. I'm going to Control C it here and see what we stop on. And it should match words that have 2 vowels following one after the other. So here we have AU as well as masks with UE, so on and so forth. All right. And so what we see here is the ability to compose these regular expressions together to form some patterns that we might expect to see in some language. And so one of the powers of these things is that our ability to compose them is just like arithmetic expressions, where, you know, it's not like we can just say 1 plus 1 and we can only use the plus operator to form an expression. We can use multiple operators together to form complex formulas or expressions, and use parentheses to say which have higher precedence and which should come first, things like that. And so the same type of concept applies to regular expressions, where if we have comp or psi, we would match any word that has competent or psi. But if we had COM in one set of parentheses, followed by P or S, followed by CI, then we would match, say, COM P CI or COM S CI, right? So when is it ever valuable to specify 0 or more repetitions? Like as you saw, as I was trying to on the fly come up with examples of where this would be valuable in searching for words, it seemed kind of hard to come up with good, meaningful examples for that. But if we imagine we're trying to match a number, and we have a regular expression that specifies the digits of a number, right? So this regular expression R will match any digit. 0 or 1 or 2 or 3 or 4 or 5, so on and so forth. So how could we try and specify a whole number as a combination of digits using only concatenation or alternation? Well, if we wanted to specify a whole number, so the regular expression to match a whole number would be the regular expression to match a digit, so any of these, or a digit followed by a digit, so that's the concatenation, or a digit followed by a digit followed by a digit, or, and you kind of get the point, right? Having to try and enumerate the possible sequences of how many digits we can represent gets pretty exhausting. And you could do this for a reasonable amount of numbers, but what makes it much easier to specify, and where you'll see this Kleene star or the closure operator often used, is, well, we can describe any whole number, right? And in an infinite number of whole numbers, actually more than we could count, by saying by composing one digit followed by zero or more representations of it, or zero or more repetitions of a digit, right? And so this gives us the ability to we can now match against an infinite number of whole numbers based on this regular expression, where if we needed to specify using only concatenation and alternation, we would have a discrete or a finite number of whole numbers that we could match against. But this allows us to match against an infinite number, right? One of the reasons why it's really nice to break our regular expressions down into simpler expressions, right? So our digit is a regular expression that has this definition. And here we're using our digit as a regular expression symbolically, right? Is because it would be very long and tedious to have to, if we couldn't specify regular definitions in this way, right? And so what we'll see is this is going to be called, what we did up here at the top, this is a regular definition where we're specifying sequences of definitions for regular expressions, and we can make use of earlier defined regular expressions in later defined regular expressions, right? So here we defined our digit, and later we used our digit and knew that it meant and could be substituted with its actual definition. So these are the three fundamental operators of regular expressions: concatenation, alternation, and then repeat zero or more times through closure. And the ability to compose these together is such a big deal here, because we can now specify patterns that will tell us whether or not some text matches or satisfies that pattern. And if you think about what is it that it makes up a programming language, well, there are rules that the tokens or the lexemes of your programming language, they can all be specified as regular expressions. And as we move forward, we'll see some techniques in how this is done. And so this is allows us to specify very complex patterns that we can write programs to match against and confirm whether or not some input text matches some regular expression pattern. As I mentioned just before, a regular definition is just like what we saw on the previous, on 2 slides ago, right? So it's this ability for us to declare some definitions. And here I'm saying the definition 1 is being defined by a regular expression 1. And definition 2 is being defined by regular expression 2. And the idea is that in a regular definition, on the right-hand side, where we make use of regular expressions here, we can use any previous definition, right? So we could use as a part of this Rn any d of n minus 1, right? Meaning that if we want to use something that we defined earlier, that's okay, but we can't use something we defined later, and we can't be defined in terms of ourself. We'll later learn some languages that allow us to specify definitions recursively in terms of their self. But one of the things that is a limitation of these regular definitions is we can only specify something that has come in an earlier definition.